Hello and welcome back to Precalculus. Last time we talked about vanilla word problems for trigonometry, and the goal for today is to continue with a little bit spicier examples. Now, last time it was pretty much the situation you see. You have a triangle somewhere, and you figure out where the opposite, adjacent, hypotenuse are, and you set up your trig formula function. It could be literally any of the six. Now, we generally aim for sine, cosine, tangent because those are kind of standard easy ones, but you are not prohibited to use secant, cosecant, and cotangent. Generally, no one does, but you can if you want to feel very special, right? Now, the goal for today is to take a look at situations when you have um, multiple triangles, similar triangles, and then also take a look at some of the basics of physics. So there is this really uh, cool problem. Again, in terms of what you would call a real life is pointless, but so here we have a hot air balloon, and that hot air balloon went up in height. We have the angle of 19.2 degrees and the larger angle of 31.7 degrees, and they want to know this difference in height. Let's call that age right there. And this is 125 feet in distance right here. So how much is this difference in height? Well, when you are dealing with these trigonometric problems, the most important part is to set up the triangle and a trig function so that the least amount of functions, calculations are used. We don't want anything that has to do with the hypotenuse, because this distance, the hypotenuse distance over here, is not given to us, and we have to figure it out, right? So that's annoying. We know that we have to deal with the height over here, so we are already dealing with opposite side, right? Because these sides, there are two of them. I'll also put the red one. I hope you see now the black larger triangle and the red smaller triangle. Both of those are opposites, right? Whether you're using a red or a black, let's use the capital opposite and lowercase opposite. And then you have the adjacent, which is the same for both triangles. And then you have the red angle, 19.2, and the black angle. So when you want to see by how much the hot air balloon went up, you can set up two tangent, right, opposite and adjacent functions. So tangent of 19.2 degrees is equal to the opposite, which is unknown, divided by the hypotenuse, which is 125. And that's from the red triangle. And you do exactly the same thing for the black triangle. Tangent of 31.7 degrees is equal to now capital opposite over 125. And the height that we are looking for is clearly the opposite minus the opposite, right? The capital opposite minus the lowercase opposite. Both of those you can calculate from the functions you wrote using tangents, right? So if you stuff all of this in the same equation, the capital opposite is 125 tangent, right? When you move 125 to the other side to get opposite alone, 125 tangent 31.7 degrees minus 125 tangent of 19.2 degrees. And this is something that you can just stuff in your calculator. Now make sure that your calculator is in degrees, because your calculator should always be in radians, because that's the way to graph the trigonometric functions. Even if you're taking your engineering course and physics course where people love degrees, right? And I use them as well. Anytime I use application like this one, the calculator is always in radians because the graphing works in radians. Even though if everything is given to you in degrees, you still have to convert into radians to graph. So I go into mode and make sure that I'm in degrees, then second quit. And then we go 125 tangent 31.7, close the parenthesis, minus 125 tangent of 19.2 to get 33.67, so 33.7 feet. Again, I can only have one decimal because my input numbers, right, 125 feet, had no decimals in it. So 33.7 feet is that height by which the hot air balloon went up. We did not calculate opposite sides at all. We don't know at which height the balloon is in comparison to the ground. We were only interested in this, well, the problem was interested, so that's why we were interested in it. The problem is interested in this extra piece of the height, right? The difference. So that's what we computed. Now it's very easy to modify, obviously. If you just compute each one of the opposite sides, the capital opposite would be the height of the balloon away from the ground. All right, so now we're going to talk about bearings, which is used to navigate the airplane and ship across the sea. And for that, we don't use positive and negative x-axis and so on. We use the sides of the world. So you have the east and the west and the north and the south. So the sides in the compass. And that's what we are going to use to show problems that have to calculate problems that have bearings in it. So let's take a look a little bit about just a little bit of a theory before we start working on problems. More where is the all right? So how does it work? Bearing. So what do we have? We have it looks like XY coordinate system, but instead of X, Y, and so, we'll put north, south, east, and west. And now, the direction in which you go, if it's on the axis, you will go due north. If you go up. Not up in the air, but forward. I mean, and then you go left and right, due west, right, due east, due south. But you can also go at the angle to any one of these. And this is where you really have to pay attention. Bearings measure angle from the closest y-axis, where everything we did so far in the course, reference angle was to the closest x-axis. So you have to be very careful with that. So if I have this direction, where this is, let's say, 60 degrees, the bearing is north 30 degrees east. You would say, hold on, what do you mean 30? Because it is 30. Angle has to be measured to the closest y-axis. So even though the angle was given with the x-axis, we don't care. We say 90 minus 60 is 30. So north 30 degrees in the east direction. Because guys, you have north 30 degrees in the west direction. That's the black one over here. Right, north, that's where you start. Then you go 30 degrees and then in the west, on a westbound, which means left. So you have to be careful about those things. Let's take a look at another one. Again, north, south, east, west. And then we have, let's say, 17 degrees. Can anyone solve this? What is the bearing? Yeah, don't all scream at once. Stop talking over each other. Just one person. Say what's on the y-axis, closest y-axis, then the angle, and then whether it's east or west, which way it goes. So, south, 17 degrees west. So you always start with north or south because those are the y-axis values. And then the angle that is that has that y-axis as one of the sides, rays. And then you either go east or west, right, depending on which way the picture is. Let's see. What do you have?
Is it south 66 degrees east?
Very good. South, 66 degrees east. Because this is the angle that we need, and that's 66 degrees because together they have to make 90. So south, 66 east. Good. Good, good, good. So now that we are able to work that out, we can figure out problems that have motion. Now, you're technically working with vectors without me telling you you're working with vectors. You leave your house and run 2 miles due west, followed by 1.5 miles due north. At that time, what is your bearing from your house? Okay, draw big so that you see exactly what's happening. So you have a north, south, east, and west. You leave your house and run 2 miles due west. 2 miles due west. Okay, let's say this is 2 miles due west. 1 mile, 2 miles. And then you go 1.5 miles due north. So you were running exactly west, and then you turned 90 degrees and you went north. So the question is, what's the bearing to from your house to you? What's the bearing? Okay. Well, you know that this is 2. You know this is 1.5. You know that you need this angle here so that you can calculate that angle the one that you need, because your bearing is going to be north, some number west, right? And that some number, the orange question mark, is the orange question mark here. So if I am able to find the angle that we see in the triangle, which we are obviously going to use basic trig, then we can just subtract it from 90 and we have the angle we need. Yay! So we have our opposite, we have our adjacent, we have our hypotenuse that we don't need now, and we can set up the tangent of this unknown theta, or whatever you want to call it. Theta is going to be opposite over adjacent. So if you apply inverse tangent to both sides to free up the angle theta, because that's what you're supposed to compute, you have to solve inverse tangent of 1.5 over 2. Now, yes, leave your calculator in degrees because it's applied problem, and we're just going to get degrees from this one. That's tangent inverse of 1.5 divided by 2, which is 36.87 degrees. Now, we could have put 37 degrees and we wouldn't be wrong, but such is life, right? So now, the angle that we need, the question mark, right, is going to be 90 minus 36.87. Right, so that will be 13 there. You steal 1 from the 0, that's going to be 3, and that's 8 minus is 53. So the angle over here is 53.13, but I could just say 53, it's okay, degrees west. 53 degrees. That's it. So north 53 west, because it bends towards the left, which is west. Now, if it bends right towards east, then it will be north and then number and then east instead of west. So I would say it's really straightforward the way it works. And pretty much all of the problems are the same. You know, someone is running or someone is driving. They're all pretty much the same problems. Try a couple of these for the homework, and then if you have questions, obviously office hours and or class time, we can discuss these problems. One more thing left for us to look at, and then chapter 4 is behind us, and that is simple harmonic motion. And I gotta love the title, simple harmonic. There's nothing simple about this. It's not simple. It's a nonlinear equation, so it's definitely not simple. I don't know who and why came up with a title, but that's okay. It's interesting to call something that is used to simplify mathematics, to call it complex analysis, right? Where it's there to make a joke pretty much of every concept we learn in real analysis. But anyway, What is the simple harmonic motion? Well, you can think of the pendulum. You can think of the weight that it's suspended on the spring or the rubber band off of the ceiling. You can think of the spring on horizontal way, pushing and pulling onto an object, therefore oscillating left and right. You can put that vertical, right, oscillates up and down. You can, as I said, also look at the, well, there are many other examples in electrical engineering, mechanical engineering, and so on, but the ones that are easy to understand with the spring and the mass, it's good, but rubber band would also do the job and so on. Well, rubber band would not do the job of pushing the object out. The spring does that. So it creates oscillation, but the rubber band can, when you stretch it beyond its equilibrium state, it does pull back inside. So it's like a half spring use. So what do I have? If we look at the horizontal one, we put some kind of weight, like be a crate of some kind, and here is a spring attached to it. Now we're going to say there is no gravitational pull, there is no friction, right? So all of this stuff here is just a crate, and then the surface on which it is so smooth that it does not make any friction. We know that doesn't happen, obviously, but the friction actually adds a whole nother term and makes a whole lot of mess of calculations. So we're just going to think about this one. And now what is happening here? Well, if you are not doing, if you don't touch the system at all, no push, pull, nothing, right? Then this crate will be what we say at equilibrium position. The spring would stretch or shrink, depending on where you started, to create the same amount of force, and the object will just stay there. But if you are to flick the object, you flick it and it starts moving left and right, at that point you have two options. One option is that the object will eventually slow down and stop because of the friction and air resistance and gravity and all that stuff. Or you will have that object oscillate forever in the same way because there's nothing to slow it down. It goes left and right, left and right. And if you think about this, these are distances. We can call them x, right? And what you have is a graph which is distance x against time t. Now you are going to say, why is my x on the y-axis? So x is the distance now. And I'm going to put the time axis on x-axis, and the displacement that we calculated is going to be on the y-axis. Now, if this is a sine wave, then it would look like this. We know the graph of the sine. Now, what is this? Well, it shows you the amplitude A, which is the furthest the block actually goes. But remember, the block doesn't teleport from this location to that location. It goes through all other lengths, right? Between 0 and maximum A over here. It goes through all possible lengths. So all of those lengths are included here on the graph on the side, and that eventually hits the furthest away point. Then it's going to keep oscillating, right? It's going to go back and it's going to travel to the next segment on the line to pick up the other value that's also amplitude. Now, for our personal understanding of everything, we put a negative, even though we know distances are never negative. But you do get that negative A on the other side. Now, it's kind of bad to write it that way, but I hope you understand the concept behind it. So this block will oscillate left and right, and because of that, we have trigonometric behavior, because those are the only periodic functions we know. So now the question is, so what are the equations that are involved in all of this mess? Well, first of all, we are going to define the distance, right? That's the distance. So distance is going to be given as a cosine omega t. Again, that's something that you learn in physics. Now, you could have the sine variant as well, but we tend to like cosine better. So, yeah. And a is the amplitude, and we know that omega is angular velocity, but omega is connected to the period. There we go. So, and by the same token, it's connected to the frequency. So, omega is going to take a role of that b from before, and what you have is that the period is equal to 2 pi over omega. So when you have so amplitude and the period, those are the only two actually that were given in there. Now you can also define the frequency, which would be 1 over the period, and that's obviously going to be omega over 2 pi. It's upside down. All right, so there's our equation for simple harmonic motion, and then we have all of the other stuff around that equation to explain and help us with the equation. So now let's say the distance d formula is given as 10 cosine pi over 6t. Find distance at t equals 3 seconds, let's say, and so find the distance, and at 3 equal to this, and then we can find the frequency, we can find the period. Okay, well, we already know that period is 2 pi over omega, so why not use it? Your a is 10, and your omega is pi over 6. So we can use our formula to calculate period, and then we flipped it inside out, and we get the frequency immediately. So period is 2 pi over omega. What was it? Okay, so 2 pi over 6, the whole thing works out to be 12. So now we have a period of 12, and the frequency is 1 over 12. So we can find the frequency, also the amplitude. Amplitude is A equals 10. That's how tall the waves are, or whatever you are observing. It will come back, right? This stuff from this box, it will come back when you take differential equations. Right now, we don't have to worry too much about it. All right, so let's pick one more word problem. Hopefully something with this. Do they even have them? Problem 60. It says an object in simple harmonic motion has a frequency of 1/4 oscillation per minute and an amplitude of 8 feet. Write the equation as a sine. Write the equation of the simple harmonic motion. Simple harmonic motion. SHM. Simple harmonic motion. All right. So what they told us is that the frequency is 1/4 of oscillation. Frequency is 1/4 of the oscillation per minute. Now, what does this mean? 1/4 oscillation per minute. Would anyone like to take a shot at answering this question and the meaning of it? Nothing? 1/4 of oscillation in the whole minute. That means that 1 minute has 4 parts, right? 1 minute has 4 parts, therefore, one full oscillation happens every 4 minutes. So that's what it means. So if one oscillation you can do quarter of oscillation in 1 minute, then you can do one full oscillation in 4 minutes. Now, why is that important? Well, one full oscillation in 1 minute, that's a period. So period is 4 minutes. And we just got the period from that simple sentence, right? We got the period. And now we're going to take a look at what we have here. One full oscillation every 4 minutes. And give me 1 second over here. So they told us to use D equals A sine omega t. Period of the sine is 2 pi. And then remember, we need this one, right? We have that formula. Whether you want to use it as a b when you did your graphing before, or you want to use it with omega, whatever, right? But period equals 2 pi over b or 2 pi over omega. I don't care which notation you want to use, right? When you are in physics, you should obviously use omega. And when you are in math, you should use b, but it doesn't really matter. It's the same thing, right? You have 4 is equal to 2 pi over omega, from where 4 omega is equal to 2 pi, and omega is equal to pi over 2. So we are able to come up with omega equals pi over 2. And your distance d is 8 feet sine pi over 2t. And there's the equation for that simple harmonic motion. You will hopefully eventually do the physics experiment where you literally count. With a stopwatch, you count how many times the pendulum swings left and right, and then that's how many oscillations you had in whatever period of time, and you can figure out from that, right? You can figure out the period. Once you have the period, you can calculate the omega, and you have the equation for that motion. When you have the equation of the motion, that means that you can determine where that little thing that oscillates, where it is at any time. And later on, through calculus, you can figure out the velocity and acceleration, right, when you learn derivatives. So it just keeps building from that point on. So that's it for these guys. The word problems. We included some of the physics at the end. And as I said, if you guys have any questions, hopefully we'll stop by the office hours and we will address all of that. Bye.